All of the problems recorded in my videos can be downloaded at statisticsworkbook.com. If you go to the website, click on the PDF, and you can download a copy of the entire workbook for yourself. Also on the website, you'll find access to all of my videos that I've produced on statistics, not only the ones uploaded to YouTube. I've uploaded over 100 videos that just aren't available on YouTube. So I hope you'll check out statisticsworkbook.com. Alright, let's begin. Hello and welcome to this first exercise in Module 13, where we're going to be looking at analysis of variance. And it's called a single factor analysis of variance because the later ones that we'll get into will allow for two factors. And this is just a completely randomized design. We'll look at a couple of different designs as we go through the exercises. So let's just get into this exercise, and we'll talk about different issues that might come up while you're doing this as they arise in our work here. So here we have White Tooth Ink is developing an additive for its line of toothpaste that is designed to whiten teeth in as little time as possible. It currently has two variations of the additive, type A and B, but only wishes to produce and market one of them. In order to determine the effectiveness of these new additives, a focus group consisting of 15 people is organized. 5 people are given type A, 5 people are given type B, and 5 are the control group, and they're given a placebo. So probably just a plain toothpaste without any additive in it. Each person is asked to use the toothpaste and record the time of days it takes before their teeth achieve a predetermined shade of white. So first of all, before we go through the exercise, let's just identify the different components of this experiment. So when we talk about what is our factor of investigation. So here our factor is really just the oops, I didn't mean to cross it out, I meant to underline it. There's the toothpaste, right? We're studying toothpastes is the factor. The treatments that we use, sometimes called the level of a factor. Well, here I have 3 treatments. I have a type A, a type B, and I have a placebo. Where's that written down here? I have placebo here, and you can see that in the data, the way it's organized. I have 3 treatments. What are our experimental units or observational units? Well, these are my 15 people, 5 in each of my treatments. So we have our experimental units are the people. And finally, what's our response variable? Or really, you can think of the response variable as being the units of measurement of your data. And so here we have our measurements. We're recording the time in days, I guess not of days, the time in days before it takes their teeth to achieve this predetermined shade of white. So our data here is measured in days. Okay, so there we've got the different pieces of our experiment all laid out. Now let's go ahead and perform our test. So anytime you're doing an ANOVA study or an ANOVA analysis, you're going to be asked to fill out an ANOVA table. And so this, I've got one sort of started way down here, so I apologize, I'm going to be scrolling up and down a few times and to complete in this table and to perform our calculations. Because as we've said, if you've watched the intro video to this section, what we're doing here is partitioning all of the variation in this data set. We're partitioning it into its 2 sources. So we have the total variation, SST, which, if you recall, the formula looks something like this, and we add this across all observations, I through NT, J through K, and we split that into SSTR plus SSE. SSTR, this is just looking across the differences between treatment means and the grand mean, plus SSE. This is just a calculation that includes only the within treatment variation. So we're just looking at the individual sample variances. So what we need to do for our ANOVA table that we're going to fill in is calculate each of these components. We'll calculate degrees of freedom. Well, not calculate, we'll determine the degrees of freedom. We'll get MSTR, MSE, because that gives us our test statistic, which is that ratio of MSTR to MSE. Then we'll find a critical value and a p-value, etc. So let's get into it. The first thing that we're going to need here, we'll start with sum of squares treatment. So the first thing that we're going to need is our grand mean. Now the grand mean can sometimes be I don't want to say tricky, but it can be an easy place to make a simple mistake. There's different ways that we can calculate the grand mean. One, the long way, is to literally just calculate the mean of that entire data set. So I have 15 observations. What's the average of those 15 observations? That can be a little bit time consuming, especially if you're in the middle of writing an exam and you've got time constraints. The other way is to calculate a weighted average of the individual treatment means. So if I calculate, let's make sure I have room here. If I calculate our grand mean as a weighted average, so there's sample size of A times the sample mean of A and B and C, and divide that by total number of observations. So this would be a weighted average of those sample means, and usually this is the best way to go about calculating the grand mean, is taking a weighted average of the sample means. If and only if those sample sizes are the same, so only if the sample sizes are the same can you factor out this n. So if NA is equal to NB is equal to NC, I can just factor that out, and I have what's left, my 3 sample means, divided by, if these 3 sample sizes are the same, that's just 3 times n, and so those n's cancel out. And so here what you can see is that only in the case where our sample sizes are equal is the grand mean just going to be the mean of the means. Now I'm sort of stressing this because it's often the case that students jump straight to that calculation right away. And that's fine, it's a shortcut, but it only works in that one case where your sample sizes are the same. In our situation here, well, it happens to work, so we can use this shortcut. So when I want to calculate that grand mean, it's just going to be 5.4 plus 5.6 plus 8 divided by 3. So our grand mean, let me find my calculator here and get it out of the way, is 5.4 plus 5.6 plus 8 divided by 3. So 6 1/3 is our grand mean. 6.33. Okay, so that's what we'll be working with. Now let's go ahead and set up this test. So our null, our alternative, we have 3 treatments. So we're testing in our null hypotheses, A and B, and well, I guess our control group, that can be called C for the control, that works. And our alternative is not all are equal, or at least one is different. Either one of those 2 alternatives is fine. And again, just like we've been doing for every test since the beginning of this, since beginning of Module 9, I guess, we've been specifying a level of significance. So let's move down, and here's our table that we're going to fill in. I need to set this up with treatment, error, and total. So we've got all of our partitioning of this is our sum of squares. This will be degrees of freedom. This will be mean squares. This will be our F statistic, our p-value, and our critical F. So now let's start in this top left corner and we'll fill this in. So we need SSTR. I'll rewrite the formulas. This is NJ x bar j times or minus the grand mean squared. And we add across all treatments. So in each of our cases, our treatment sizes are the same. So that's just going to be 5 times, now here I'm going to be working with these 3 sample means. So 5.4 minus always that same grand mean squared plus 5. This one now is 5.6 minus 6.3 squared plus 5 times 8 minus 6.3 squared. Okay, now let's get that calculator out again. Now, where can I put this? I don't want to hide my calculations. Maybe right there is okay. Okay, so I'm gonna cheat a little bit. I'm gonna factor out that 5. So I'm gonna calculate all of the squared differences, add those together, multiply it by 5 at the end. So I can skip a couple of button presses here. So let's clear this. Open the brackets. 5.4 minus 6.33. Close that bracket squared. Plus, open the bracket, 5.6 minus 6.33 squared, plus, open another bracket, 8 minus 6.33 squared equals, and then finally times it by 5, 20.93. So here's SSTR 20.93. So I come down to my table and we'll fill this in. 20.93 degrees of freedom on treatment. This is K minus 1. We have 3 treatments, type A, type B, and the control group, just as we have 3 means in that null hypothesis. So our number of treatments here is 3. So 3 minus 1 is 2. Finally, mean squares for treatment is simply SSTR divided by, why can't I move that? Get out of the way. What's going on here? Okay, let's just work with it. 20.93 divided by 2 is 10.47. 10.47. Okay, good. We've got that done. Let's go on to the next row. Sum of squares error. So let me just clean up some space here. So SSE, for this formula now we're adding again across our 3 treatments. This is NJ minus 1 times the sample variance squared. So I'll write this out. So now I'm looking at, here I've got standard deviations. So this is going to be 5 minus 1 times 1.1 squared plus 5 minus 1 times 1.5 squared plus 5 minus 1 times 1 squared. And once again, we'll get this annoying calculator that for some reason won't move. No, okay, I guess it'll stay there. So here's 1.1 squared. I'll factor out that 5 minus 1 again. It'll just make things easier. So 1.1 squared plus 1.5 squared plus 1 squared equals, and now we multiply it by that 5 minus 1, or 4, so times this by 4, 17.84. So we've got our sum of squares error, 1784. Degrees of freedom for error is NT minus K. NT, we had 15 observations. K is still 3, so this is going to be 12. And finally, our mean squared error is 17.84 divided by its degrees of freedom. 1784 divided by 12. 1.49. Good. Now, as much as we've got everything we need now for our F statistic and p-value, it's always common convention to complete that ANOVA. So if we want sum of squares total, here we can just simply use our calculator and add up SSTR and SSE. So this is going to be 20.97 plus SSE is 17.8. Is it 84? I don't know. Oops, what's happening there? 17.97 plus 17. I think it was 84. 59.78. That's not right. What's going on with my calculations here? My gosh. Clear. 20.94 plus 17.84 equals 38.78. That's better. 38.78. Okay, degrees of freedom, nt minus 1, or 15 minus 1 is 14, which should also always be the sum of the degrees of freedom above it. So that's also 12 plus 2. Okay, now we can find our our F statistic, which is F is simply MSTR divided by MSE. So I'll get our pesky calculator that's not working for me today. And 1047 divided by 149. 1047 divided by 149. So 7.03 is our test statistic. Let's find our critical value first. So this will be alpha's 0.05, and this is from a distribution that has 2 degrees of freedom in the numerator, right? 2 degrees of freedom on treatment, and 12 degrees of freedom in the denominator. That's coming from here. So now if we go to our F tables, I want 2 degrees of freedom in the numerator, and let's see, 12 degrees of freedom right at the bottom, 12 degrees of freedom in the denominator. So this gives us, we're right in this block of numbers here. Here's our probabilities. So there's 0.05. So that corresponds to a critical value of 3.885. So there's 3.885. Now let's get our p-value. So again, we have a test statistic of 7.03. If we come back to our relevant section here, 7.03, well, this is larger. It's larger than the largest value. So our p-value is going to be smaller than the smallest value. So our p-value is going to be something less than 0.01. So our p-value will be something less than 0.01. So what is our conclusion to this test? Well, we're looking at a test across means. And up until this point, it's taken a lot of students this long in the course to get drilled into their heads that when we're doing a test on equalities, your critical values are T alpha by 2 or Z alpha by 2. Your p-values are always some probability times 2. And now, finally, once you've got all of that figured out, now it no longer applies for this type of test. Now, effectively, what we're doing for this analysis of variance is an upper-tailed f-test. So I have an f distribution, something like this. I have, here's that critical value that corresponds with an area of alpha 0.05 in the upper tail, and that defines our rejection space. We are effectively testing a hypothesis. Now, don't ever write this. You'll probably lose marks if you ever write this. But effectively what we're testing is to see is MSTR statistically greater than MSE or not. Because if MSTR is statistically greater than MSE, then that is what gives us evidence that those treatment means are sufficiently far apart that they probably came from a different distribution, either 3 distributions or at least two distributions. Now, again, you'll never write this, but that's the methodology that we're using. We're doing an upper tail f-test to determine whether or not this is statistically greater than this. In our case, our test statistic is somewhere way up here at 7. It's greater than our critical value. Our p-value is certainly less than our level of significance, and so here we certainly have sufficient evidence to reject this null hypothesis. Which of course then brings us, that's so messy, brings us to another point, is that, well, if we reject this null and we say, okay, not all of them are equal, or at least one of them is different, well, that brings up the next question. Which one is different? So this is where we will perform this Fisher's LSD. Now, I'm already almost 20 minutes into this video, so I think I'll end it here. We've done enough for one video, and I'll start up right where we've left off here to perform this Fisher's LSD, okay? Fisher's least significant difference. Okay, so I'll end it here, and we'll see you again soon. Okay, bye-bye.